Excuse me, your microphone is off.
Sorry. Okay. Oh, I'm sorry. Yeah, so I was just yeah, basically this is the algorithm that we discussed last time. There is a proximal gradient step followed by an extrapolation step. And the interesting thing is the choice of this theta t, and we will see that how this theta t plays the role in the proof. But last time we showed that this theta t is very close to t over t plus 3. And we can show this by induction. And in fact, we can show that this theta t is lower bounded by this numerical number t plus 2 over 2. Okay. This will be helpful in the proof. And when we apply that accelerated algorithm to solve a composite optimization problem, so f equals to f plus h, right? Well, this part is convex and smooth, and the h part, as we discussed before, this h is a convex and possibly non-smooth function. Okay. Normally, it is a regularizer. So we applied that algorithm. Apply this algorithm to solve this problem. Now, suppose we use this step size as a standard step size, 1 over L. L is the smoothness parameter of this function, f. Okay. Choose this step size, then we will have this convergence rate. The function value gap decays at the rate 1 over t squared. Okay. And last time we discussed that this is much faster than the convergence rate of the standard proximal gradient method. Okay. The standard proximal gradient method's convergence rate is roughly 1 over t, but here is 1 over t squared. So it's a huge difference. And today we will see how to prove this result based on all the technical tools that we have developed so far. And recall that when we introduce the standard proximal gradient method, we have shown, well, we have proved the following fundamental inequality. Okay. So this is done in lecture 5. So this key inequality basically characterizes the inequality about 3 points. X is an arbitrary point, and X and Y are 2 arbitrary points, actually. So X and Y are arbitrary. And this Y plus is defined as starting from Y, take one more proximal gradient step. Okay, so Y plus is the outcome of this proximal gradient update starting from Y. Now, given these 3 points, X, Y arbitrary and Y plus defined in this way, they would satisfy the following inequality. So the function value at Y plus, subtracting function value at X, is upper bounded by these two, the difference of these 2 quadratic terms. And previously we have shown that with this lemma, by setting X and Y plus to different values, we can prove the convergence rate of the proximal gradient method. But this lemma only works for the proximal gradient method, because here the way we define Y plus is only one step of proximal gradient method. And this does not apply to the accelerated method, because in the accelerated algorithm, we have two steps. Like we have proximal gradient descent followed by an extrapolation. So this is very different from the proximal gradient method. Therefore, we will need to kind of generalize this lemma to the accelerated setting. Okay. So this is the key lemma for the convergence analysis of the accelerated proximal gradient descent. So you can see it's much more complicated compared with the previous lemma for proximal gradient descent. But the overall structure is kind of similar because if you look at this inequality, it is a kind of a, you can understand the left-hand side as a Lyapunov function, okay, at time t or at time t. It is basically something to the something to the power of 2, the L2 norm of this vector u to the power of 2, plus the function value difference. Now, if you compare with this lemma for proximal gradient descent, the structure is similar. If you move one of these quadratic terms to the left-hand side and move this function value term to the right-hand side, okay, then we will also have a quadratic term plus a function value as the Lyapunov function, right? So the overall structure would is similar, but these specific terms, they are very different. Okay, now let's go back to this lemma. Now this lemma says that, first of all, let's define this ut. What is this ut? Well, it is a vector defined as a linear combination of xt, x star, and xt minus 1. Right. X star is the minimizer of this optimization problem. xt minus 1 are the iterations generated by the accelerated algorithm. Okay. So ut is a linear combination of these 3 vectors with different coefficients, and the coefficients are depending on the theta t minus 1. Right. So this theta t is here, right? It is involved in this momentum parameter. Okay. So define such a ut. Then for that algorithm, we can show that the following inequality holds. So it's ut plus 1 square norm square plus theta t square over L, 2 times theta t square over L, multiplied by the function, the optimality gap of the function value. Okay. This entire left-hand side is monotonically decreasing, right? So on the right-hand side, it is exactly the left-hand side, but reducing the time index by 1. Okay. So this inequality essentially says that such a Lyapunov function is monotonically decreasing. So this is the Lyapunov function associated with the algorithm. Okay. So the left-hand side is basically decreasing over the time t. And then we can utilize this inequality to do some analysis. This is similar to the result in gradient descent. In gradient descent, we don't have these terms. So there, our claim would be the function value, the objective function value is decreasing. we don't have theta t, we don't have this quadratic terms. So we only have that the function value is decreasing, monotonically decreasing. But once we add accelerations, the function value may not be monotonically decreasing. But if such a Lyapunov function, so this is the potential of this algorithm. Such a Lyapunov function will be monotonically decreasing. Okay. And let's first, so based on this lemma, let us first derive the convergence rate of this algorithm. And later on, we will show the proof of this lemma. Okay. So what we do is that because this is this inequality is monotonically decreasing over t, so we just keep unrolling this inequality, right? So the left-hand side is t plus 1 and less than something in the at time t, but we can keep unrolling this less than equal to the same terms, but at time t minus 1 until we reach the starting point. Okay. So what we get is that the left-hand side, this is the Lyapunov function at time t. Right, so the left-hand side, so this term will be less than equal to the term at t equals to 1. Okay. And then we can drop that. Here we dropped that ut square term because it is a positive term, so we can simply drop it. Right. So therefore, directly utilizing that lemma and unrolling that inequality, we can have this inequality. And then we can, based on the definition of this u vector, this u1 is essentially x1 minus x star. So you can just check the definition of this u vector. And theta 0 is simply 1. So everything on the right-hand side, it will be very simple. And then for the right-hand side, we can bound this term. We can bound this term by using lemma 7.7.4, setting y0 and x0 equals to x0. Okay, so utilize this lemma. If you set this x and y to be equal to x0, the starting point of the algorithm, then we can get this bound. Okay, so this directly comes from 7.4. Right? The function value difference is bounded by the difference of two quadratics. Okay, here's the function value difference bounded by the difference of these two quadratic terms. And then rearranging this inequality, we can show that basically the sum of these two terms will be bounded by the x0, the distance between x0 and x star. Okay. So this is to say that the entire right-hand side is simply bounded by x0 and the minus x star, the distance between these two. Therefore, we can further upper bound this term by this term. And then combining these two bounds, we can claim that the left-hand side is bounded by the square distance. The initial the distance between the initial point and the x star. So from here, we can solve for this function value difference. This difference will be bounded by the initial distance divided by 2 times theta t minus 1 to the power of 2. And then we use this fact 7.2, which says that theta t is lower bounded by t plus 2 over 2. Okay, so plug this into that inequality. Okay, because that is a lower bound of theta t. So this is compatible with this inequality. Here we have less than equal to, right? And theta t is in the denominator. So we can plug in a lower bound. And then that is further less than equal to such a term. And because of theta t, we get t plus 1 to the power of 2 in the denominator. Okay, so because of this theta t square, theta t minus 1 square, we can have accelerated convergence. So you see that this acceleration indeed comes from the choice of theta t. And it is based on this key lemma. This key lemma shows that once we add that momentum term properly with this specially chosen theta t's, we can have such a nice Lyapunov function. And this Lyapunov function will give us convergence rate that characterizes, that depends on theta t square. Okay. So the proof, so based on this lemma 7.5, the proof of the convergence rate is actually very straightforward. Simply unrolling the inequality and then rearrange the terms, we can get this convergence rate result. And then in the end, this theta t in the denominator can be simply bounded by t plus 1. So the key question is how do we prove this lemma 7.5? So let's take a look at the proof of this lemma. The proof of this lemma will be based on the lemma 7.4, based on this lemma that we established for proximal gradient descent. So what we do is we set y to be yt. We set x to be the convex combination between x star and xt. And this convex combination is based on this coefficient 1 over theta t. Because remember, in 7.4, x and y can be arbitrary 2 points. Right? X and y, these 2 points can be arbitrary. And y plus is something that based on y. So x and y can be arbitrary. So we are allowed to choose x and y in this way. Okay. Now, once we choose x and y in this way, and plug it into 7.4, we simply get the following inequality. Now here, because y is yt, y equals to yt, and let's go back to the algorithm. So y equals to yt, and then y plus is the starting from yt, we do one step proximal gradient update. Okay. Now based on the acceleration algorithm, based on this algorithm, starting from yt, after one step of proximal gradient update, we get xt plus 1. We get this one. That's why, so here, this y plus is essentially xt plus 1. Okay, so that's why here we will have fx t plus 1. And then this term is fx. This term is fx. And the following two quadratic terms are simply plug in all these definitions. So this exactly comes from the lemma 7.4. Now, in the next step, this is an equality. So what we are doing is simply try to rearrange these terms. I think what we do is pull out this common factor, theta t over -1. Pull this factor out of these quadratic terms, so we can get these terms. And we can see that. So first of all, this term, this is exactly what we called negative ut plus 1 because it's a linear combination among x star, xt, and xt plus 1. So this is exactly negative ut plus 1, following the definition of ut plus 1. But the first term is different. The first term is a linear combination among x star, xt, and yt. So we have a yt instead of xt plus 1 here. However, in this accelerated algorithm, yt is given by this extrapolation step. Okay. Yt equals to an extrapolation between these 2 points, xt and xt minus 1. Right? This is the algorithm. Right? So yt plus 1 is an extrapolation between these 2 points. Right? Okay, so the algorithm gives us this equality, so we can plug in this equality and then replace this yt by whatever on the right hand side. Okay, so replace yt by these terms, and then you simplify, combine all the similar terms. You will see that this term is exactly what we called ut. Okay, so plug in yt, and this term will become the ut. So we get this inequality. We get this inequality. Okay. So it starts to look familiar to what we have seen in 7.5. Now the next one is to handle this term. This is a bit complicated because it's f evaluated at a convex combination of 2 points. And this reminds us of the convexity because f is convex, and inside we have a convex combination. So naturally we can bound this term by convexity. So this term by convexity can be upper bounded by the convex combination of these two function values. Right. And then from this one, we can further claim that this term subtracts the function value at xt plus 1 would be less than equal to, basically less than equal to the right hand side subtracting ft plus 1. Okay. And then the right hand side can be further simplified into this form.
Now, let's see. The left-hand side is what we have in this inequality, right? Here is fxt plus 1 minus this one. Here is the other way. So it's the negative of that term. Okay. So we can combine this inequality with the previous inequality. Right. So this here we show that fxt plus 1 minus f, right? This is this entire convex combination is less than equal to L over 2 theta t squared ut squared minus ut plus 1 squared. Right. Here I copy this inequality. And then this inequality says that the negative of this term is bounded, upper bounded by this term. So what we can do is we can multiply both sides by -1. Then we will have fxt plus 1 minus this term will be bigger than or equal to the negative of this term. So we can further lower bound this term by the negative of the right hand side. Okay. So plug in the right hand side to the lower bound and simplifies things. We eventually we will get this term. Eventually we will get this term. And in particular, theta t squared minus theta t, it actually equals to theta t minus 1 to the power of 2, based on how the theta t is defined. Based on this recursion. Based on that recursion, this term is actually theta t minus 1 squared. So in the end, we proved this lemma 7.5. And you can see that the way we construct that theta t is really critical. It's very critical. The structure is very especially chosen so that everything can go through here. So that's why we call that a magic number. So it's very hard to come up with this idea at the very beginning. So see that the choice of theta t, right? The momentum parameter needs to satisfy these special structures, and also it also needs to satisfy that bound so that here we can get an accelerated convergence. Okay. So although this algorithm looks very simple, it's just one additional extrapolation step, but it is very, very carefully designed so that it can get an accelerated convergence for the entire class of convex and smooth functions. Yeah, so this is the proof of this key lemma. This is proof of this key lemma. So basically, for all the optimization algorithms that we have seen so far, the key concept of the proof is to build something, always build the optimal function. Sometimes this could be the function value, objective function value of the problem. for gradient descent and for proximal gradient descent. But for this accelerated method, the Lyapunov function is much more complicated. So it takes this complicated form. And so this is for convex and smooth functions. We also have a result for strongly convex and smooth functions. So this is the accelerated algorithm for solving strongly convex and smooth functions. We can see that the way we choose the momentum coefficient is very different. Now we are using a constant momentum. This is a constant that does not depend on t anymore. And so this is chosen as square root of kappa minus 1 over square root of kappa plus 1. Well, this kappa is the condition number of the problem. It's L over mu. Therefore, here we are injecting a constant momentum into this accelerated algorithm. And then one can show that for such a strongly convex and L smooth problem, if we pick such a standard step size, then the convergence, the function value gap will diminish geometrically fast. And here, this diminishing parameter is 1 minus 1 over square root of kappa, instead of 1 minus 1 over kappa, compared to the convergence rate of the proximal gradient method. And this is faster than the convergence rate of proximal gradient method because of this square root. Okay. And this is a table that summarizes all the convergence results of accelerating methods in different cases. So for convex and smooth problems, we proved accelerated convergence rate 1 over t squared. And correspondingly, the iteration complexity is 1 over square root of epsilon. Epsilon is the target accuracy. But for strongly convex problems, the convergence rate is 1 minus 1 over square root of kappa to the power of t. And then because of this dependence on square root of kappa, the iteration complexity is square root of kappa times log of 1 over epsilon. This is much smaller compared with the iteration complexity of proximal gradient descent. For that one, we have kappa times log 1 over epsilon. So it's kappa versus square root of kappa. So I think this is everything about this accelerating method. So in the homework, you will need to implement this accelerate, like we discussed last time. You need to implement this accelerated algorithm, and it's actually very simple. It's based on what you implemented previously. Okay? You have done the proximal gradient part. Based on that, in your code, maybe you want to keep track of the previous 2 iterations, so that you can do this extrapolation step. And then in the examples, we will try different choices of these momentum coefficients. Compare the performance. Okay.
And then we can start to talk about the lecture 7, which is a very different technique. It's not it is a very interesting technique, and sometimes we can use this technique to smooth the non-smooth problems. Okay, so this lecture is focusing on the technique called smoothing. The idea is very simple. If a function is not smooth, can we smooth it and then solve it as a smooth optimization problem? Okay. We'll first talk about smoothing. What is the concept of smoothing? And then what are the technical tools we can use to build a smooth approximation? In the end, once we have a smooth approximation, how can we solve that? What algorithms can we apply, and what are the convergence guarantees we can have? So in the previous lectures, when we talk about non-smooth optimization, we mentioned a subgradient method. Say, let's look at minimize fx. Well, f is a convex function, but not necessarily differentiable. It could be Lipschitz, but not necessarily differentiable and smooth. And previously, when we introduced the subgradient method, right? So when f is not differentiable, we can compute the subgradient and do subgradient descent. For this method, for the subgradient method, we have shown that the iteration complexity is 1 over epsilon to the power of 2. So to attain an epsilon accuracy, we need this many iterations. However, in the previous lecture, we just showed that, in contrast, if the function is smooth, if the function is convex and smooth, then we can apply accelerated gradient descent. And this one attains a much lower iteration complexity. It is 1 over square root of epsilon. And you see these two has this huge gap. Like the second one is much faster. The complexity is much lower compared with the subgradient method. Therefore, we can see that optimizing the smooth functions is significantly better than optimizing the non-smooth problems using subgradient. So the question is, can we somehow transfer the non-smooth optimization problems into a smooth one, and then using these accelerated algorithms to solve the problem? And there are some existing studies to show that if the algorithm can only access to the gradients or subgradients, then this complexity for non-smooth problems is the worst case complexity. So one cannot improve this complexity in general. So here we will talk about this strategy. We can first approximate the non-smooth problem by a smooth problem. Okay, if you give me a non-smooth problem, I don't want to solve it directly using subgradient method. Right? Instead, I can first approximate the problem by a smooth problem. Okay. If I can find a smooth problem that is very close to my original non-smooth problem, then hopefully I can instead solve
this smooth problem and quickly get a good solution. But once we have a smooth approximation, we can instead optimize the smooth approximation, maybe using the accelerated gradient method that we just introduced. Okay. So the first question is, what is a mathematical, formal mathematical way to smooth a non-smooth function? And we will introduce such a definition to quantify such a smooth approximation. Okay, so for a convex function f, we will call it alpha beta smoothable. So that sounds like this function can be smoothed according to these two parameters, alpha and beta, in a certain way. Okay. So how do we specify this? We call this function alpha beta smoothable if for any mu bigger than 0, we can construct a convex function f sub mu such that this function f is close to f sub mu in the following sense. First of all, the first criterion shows that fx is lower bounded by f mu and upper bounded by f mu plus a small constant. It's upper bounded by f mu plus beta times mu for any x. Okay, so this has to be held for any x. And the second of all, for this convex function, for this approximated convex function f mu, it is alpha over mu smooth. Okay. So if you look at this definition, basically, we say a function f is alpha beta smoothable if we can find a smooth approximation f mu. Okay. We can find an alpha over mu smooth approximation such that this approximation is close to the original function f in this sense, right? So f can be lower bounded and upper bounded by f mu in this form. So you can see this parameter beta controls the approximation accuracy. If beta is very, very small, then the first inequality says that we have a very accurate approximation. And then the alpha controls the smoothness of your approximation. And here, this parameter mu controls the trade-off between approximation accuracy and smoothness. If you choose a very small mu, again, it implies that we are looking for a very accurate approximation. But instead, the function may be like the smoothness parameter may be huge. And then this function may be ill-conditioned. Okay. So this is a trade-off between approximation and smoothness. And sometimes we call this f mu a 1 over mu smooth approximation of the function f with parameters alpha and beta. But essentially, we're just looking at these two quantifiable conditions. Okay. So this is only a definition. We haven't talked about how to construct such a function f mu. It's just a definition. If we can find such a function f mu such that it approximates the original function well, and also it is smooth, okay, then we call it alpha beta smoothable. Then we call this function alpha beta smoothable. And this is a very intuitive example to illustrate this smoothable or smoothing idea. Let's look at the absolute value function, or the L1 norm. The L1 norm is simply the absolute value function if in one dimension, in the case of one dimension. So the blue line is the L1 norm. It is not differentiable at this point, therefore it is not smooth. But we know it's Lipschitz continuous. So this is our original function, z, the absolute value of z, the L1 norm in the one-dimensional case. Now, this red curve illustrates the idea of how to construct a smooth approximation of this non-smooth function. So what we do is the following. So we have this L1 norm. Okay. And apparently the issue is this non-differentiable point at the original point. Now what we do is approximate, because this is a non-differential point. We want to find a function that is differentiable at 0 and sort of close to this. This is like a triangular shape, right? It's going down and going up. So a very natural idea is to use a quadratic function to approximate it. We use a small quadratic function. And then we stop at here. We stop at a certain point. Beyond that, we still use the same straight line in parallel to this to the absolute value function. Right. So these, okay, maybe I should use a different color. So we use a straight line. Okay. So you see the red part is a quadratic function to make the function smooth, differentiable smooth around the original point. And then we stop at a certain point, and then we connect this function to the straight lines again. So the green curve, the green part, is parallel to these two straight lines. Okay. So this is what we have here. Okay, we call this Huber function. Okay. And we call this function h sub mu z. Now basically this function is analytically given as follows. When z is between negative mu and mu, we use a quadratic function. How do we specify that? It's z squared over 2 times mu. Okay, and so this is a quadratic function. And outside this region, we use two straight lines. So the function is absolute value of z shifted by mu over 2. Okay, so shifting the blue curves by mu over 2, so that these two lines will connect to this quadratic function. So in the end, this h mu z function, when we plot it, it looks like this. So first of all, it's very close to the blue, right? This L1 function, very close. Actually, you can just decrease this mu, and then you will see that this function will getting closer and closer to the blue function. Okay, so this mu controls the approximation accuracy. So this is a very simple idea of smoothing. It's essentially around that non-smooth point, we can use some quadratic functions to make it smooth. Right? And then for the rest part of the function, we do not change it. Okay. Now for this function, we can show that because we have the analytical form, it is easy to show that it satisfies this inequality. So the absolute value function. So the absolute value function is lower bounded by h mu z. Okay. In this figure, is clearly the blue curve is above the red curve. So it's lower bounded by h mu z. And actually, it is also upper bounded by h mu z plus mu over 2. So if you shift this blue curve above by mu over 2, then the red curve will be above this blue curve. Okay, if you shift this entire thing by mu over 2, then it will be above this absolute value function. So this absolute value function is between these two smooth approximations. And moreover, for this function, we can show it is 1 over mu smooth. So it's differentiable, and the gradient is 1 over mu Lipschitz continuous. The reason is that it has this quadratic part. It has this quadratic part. So it is essentially a quadratic function around this original point. Okay, so this gives a very simple example of constructing a so-called alpha beta smoothable function. And in this case, the alpha equals to beta equals to 1/2. Beta is here. And alpha equals to 1. Right, according to these definitions. But the essential idea is that whenever we see a non-differentiable point, we can try to approximate the function using some differentiable components. So this is a one-dimensional construction. We use this one-dimensional Hoover function to approximate the absolute value. But for the L1 norm, we can simply add them up. For L1 norm, we simply approximate the absolute value of each coordinate by this Hoover function, and then sum them up. So in this way, we constructed a smooth approximation of this L1 norm. And in particular, for such a construction, we can show that the L1 norm is bounded by this f mu function in this way. Well, we have n times mu over 2. on the right hand side. This n is the dimensionality of this vector. And also it is a smooth function. So 1 over mu smooth function. And so therefore we can claim that the L1 norm is 1 n over 2 smoothable. So this is our alpha, this is our beta. Another example is the L2 norm. It's the L2 norm. Because even in 2 dimension, in 1 dimension, L2 norm equals to L1 norm. But even in 2 dimension, L2 norm is not differentiable at the origin point. So this is a illustration of L2 norm in the 3D space. So the dimensionality is 2, and the z-axis is the value of the L2 norm. So here we have a non-differentiable point. And we consider such a function f mu x. It is defined as square root of x, L2 norm of x to the power of 2 plus mu square, and then outside the square root we have minus mu. Okay, we simply construct such a function. You can see if mu equals to 0, we simply reduce to L2 norm. Right? So if mu equals to 0, f mu equals to f. And moreover, this turns out to be a valid, smooth approximation of this L2 norm function. First of all, this function is less than or equal to the L2 norm. So this function is less than or equal to L2 norm because f mu x, this square root, is less than or equal to the L2 norm plus mu. Okay, by this fundamental inequality. Right. So for any two positive numbers, their sum squares taking the square root is less than or equal to a plus b. Okay, for positive numbers. Therefore, this shows that f mu is less than or equal to L2 norm. And moreover, L2 norm is less than or equal to f mu plus mu. Okay, because L2 norm is less than or equal to this one, and this one is less than or equal to, and this one equals f mu plus mu. So this shows that f mu x is a valid approximation of this L2 norm. Moreover, this function is 1 over mu smooth. You can check the gradient of the Hessian and show this property. It's 1 over mu smooth. So this shows that the L2 norm is 1 smoothable. The L2 norm function is 1 smooth. So it's relatively easy to approximate, to smooth this function. But for L1 norm, it's 1 n over 2 smoothable. So it's very different, right? So this beta scales with the dimension n. This means that it is relatively hard to smooth a high-dimensional L1 norm function. This is the L2 norm. And we have a, let's see. Yeah, we have this, another interesting example. It's the max function. Function is maximum, taking the maximum value between the two coordinates. Assume we are considering the two-dimensional vector. So the function is defined as the maximum of these two coordinates. And the function looks like this in the 3D space. There's a non-differentiable line here. What we can do is to smooth this function using log sum exponential that we introduced before. Okay. So let's define this f mu x. F mu x equals to mu times log. Inside we have sum over all the coordinates. Well, for each coordinate, we do exponential to the power of xi over mu. Okay, so it's a summation over e to the power of xi over mu. And in the end, we subtract mu times log n.
You care about well, I mean, not obviously.
So we define such a f mu function. And we can show that this function is less than, first of all, it's less than or equal to the original function. And moreover, this maximum function is further upper bounded by the function f mu plus mu times log n. Okay. So this shows that such a function is also a valid approximation of the maximum function. And you see that this construction is highly non-trivial, because here we have a maximum of these two functions, but in the construction we use log sum exponential to approximate the maximum in a certain way. And moreover, we can show that this function f mu is also 1 over mu smooth. But you can check the derivative, or you can check the Hessian matrix. Therefore, we can claim that for such a piecewise linear function, max over xi, this function is 1 log n smoothable. Okay. This beta depends only on the log n, so it's not a very critical number. And actually, in practice, these functions you can use these functions to approximate these maximum functions or L1 functions, if you don't want to handle these non-smoothness. Yeah, and we have some basic rules for these smooth approximations. The idea is that, say we have two smooth approximations, f mu1, f mu2, and with different smoothing parameters, approximation parameters. Then a linear combination of these two is also a valid smooth approximation. But the parameters will be different. Here we have a linear combination, so the parameters will also subject to a linear combination of these original parameters. So this is like a linearity of this smooth approximation. And we further have this affine transformation. Yeah, if F mu is a smooth approximation, then H AX plus P. So inside we have affine transformation. This is also an approximation of the function, but the approximation parameters will depend on this linear transformation and basically depends on the spectral norm of this linear transformation. For example, we have shown that this function is a 1/mu smooth approximation of the L2 norm function with parameters 1 and 1. So alpha and beta are 1. Instead, we can also look at such a smooth approximation. Well, X becomes AX plus B. And then using that affine transformation rule, we can conclude that this is also a smooth approximation, but with parameters alpha equals to the spectral norm of A to the power of 2. Okay, so the approximation depends on the spectrum of this linear transformation. And this is another way to look at this smoothing the absolute value function. So we can rewrite the absolute value function as the maximum between x and the negative x, assuming this is a one-dimensional case. So this is exactly equal. Or equivalently, we can write this as max over A times x. Well, A is 1 and a negative 1. Right. So it's this 2 by 1 matrix multiplied by a scalar x. And then previously we have shown that this is a good smooth approximation of the maximum function. Okay, and then here we simply have a maximum function subject to a affine transformation. So we can use the affine transformation rule to show that this approximation is also a smooth approximation of the absolute value function with a different set of parameters. Basically, the same function, this function, it can approximate two different functions. Okay. One is a maximum function, and the other one is absolute value function. Okay. But we are there, but it is a approximation with different smoothing parameters. Okay. Intuitively, the absolute value, like considering this form, right? The absolute value function is a special case of the maximum function. So we can use this. We can still use this function to approximate it. Okay, and so throughout all these examples, we see that for different simple functions, okay, for different simple non-smooth functions, we can find a good smooth approximation in a certain way. And the way we approximate them are very different. Like L1 norm, we use the Hooper function to approximate it. L2 norm, we do it in this way. And for the maximum function, it's totally different. So the ultimate question is there a way, is there a systematic way to construct a smooth approximation of a non-smooth function? Right? Like given all these examples, we are approximating them in very different ways. So is there a universal way to construct such a smooth approximation? So what is the right mathematical operation that we want to introduce for this purpose? So in the next lecture, we will discuss this technique, which we call the Moreau envelope. It's very similar to the proximal mapping that we introduced before, but they are very different. Okay, so I think I will stop here, and you can work on the next homework problem. Okay, and let me know if you have any questions. So I will see you next week.
Thank you.
Okay, thank you guys.
Thank you, class.